In this video, I'm going to introduce the topics of thermochemistry and thermodynamics by first talking about energy, enthalpy, work, and heat capacity. So thermodynamics is the study of energy and its transformations, and this is a topic that we will be covering for the next couple of chapters. Thermochemistry, which is the topic of this chapter, is the study of the changes in energy that accompany chemical reactions in particular. So some common chemical reactions that are used to produce the energy that we use, so for example to heat our homes, to run our vehicles, are combustion reactions. So for example, the combustion of coal and natural gas help to heat our homes. The combustion of gasoline and fuel help to move us in our vehicles. So the energy that is produced when combustion reactions occur is what we can call chemical energy. And the amount of chemical energy that a reaction can produce is dependent upon the way the atoms are bonded together. So stronger bonds that are broken are going to be able to release more energy as that reaction proceeds. Now, the internal energy is the sum of all kinetic and potential energy of an object. So if we have a reaction like this one here, there's going to be a change in the internal energy when the internal energies of the reactants are different than the internal energies of the products. So in this case, we have two hydrogen molecules, one oxygen molecule, and they react to produce two water molecules plus some energy. So the reactants in this case have more energy than do the products, right? Because as the products are produced, they are releasing energy. So that means that the reactants had more energy to begin with. And that difference in energy here, the energy released, is going to be the difference in the internal energies of the products compared to the reactants. So remember that thermodynamics is the study of energy and its transformations. So there are three laws of thermodynamics. Well, there are actually four because there is a zeroth law. But we're going to start with the first law of thermodynamics, which states that energy cannot be created or destroyed, but can only be changed in form. So for example, chemical energy can be turned into thermal energy, potential energy can be turned into kinetic energy, and so on. And the total energy of the universe is constant, so energy cannot be created or destroyed. Now the universe is made up of what is called the system and the surroundings. Now the system is defined as the part of the universe that we're interested in. So usually the reaction that we are conducting within some kind of container, maybe a beaker, and the rest of the universe is considered the surroundings. And that can also include the container in which the reaction is taking place. So the change in the energy of the universe is going to equal the change in the energy of the system plus a change in the energy of the surroundings. And since energy cannot be created or destroyed, the overall change in energy of the universe has to equal zero. So in other words, if we just want to compare the energy changes of the system compared to the surroundings, the change in the energy of the system is going to equal the negative change in this energy of the surroundings. So an example of this could be a combustion reaction that we've talked about previously. So if the reaction is giving off heat, that means that the system, so the reaction itself, is decreasing in energy, right? So if that system is decreasing in energy, then the surroundings must have the opposite sign, so it must be increasing in energy. So heat is one way that energy can move between the system and the surroundings, but work is another way that can happen. So the energy of a system is the capacity to do work or to transfer heat. And heat is the kinetic energy that is transferred from one hot body to a colder body, right? So heat's always going to go from a hot place to a cold place. And we can express that mathematically. So the change in the internal energy is going to be the sum of the heat, Q, and the work. And work is defined as a force times a distance. So if we zoom up to this table on the right, we can consider two different situations. We can consider processes that increase the energy of the system and processes that decrease the energy of the system. So a process that increases the energy of the system, in that case, the surroundings are going to be hotter than the system, and so heat is going to flow into the system from the surroundings. And in that case, Q is going to be greater than zero. And also we're going to have surroundings that do work on the system. Right? So in that case, W is going to be greater than 0. And if we look at our equation here, delta E equals Q plus W, if both Q and W are greater than 0, then we're going to have a positive delta E, which means that the energy of the system has increased. Now, processes that decrease the energy of the system are when the system is hotter than its surroundings. So heat is going to flow from the system to the surroundings. So again, that was like a combustion reaction that produced heat. So in that case, we're going to have a Q being less than 0, and a system that does work on its surroundings also fits into this category. So W is going to be less than 0. And again, if we go back to our equation, if we have both a negative Q and a negative W, the change in internal energy is also going to be negative. So I just want to give you a quick example of what it means for a system to do work on the surroundings. So in the previous chapter, we talked about gases, and we know that if we increase the temperature of a gas, then that's going to increase the volume of that gas if it's in a flexible container. So for example, if we have a gas within a balloon, we have it initially at room temperature, and then we heat up the gas, then what's going to happen is that balloon is going to increase in volume. And because the volume is increasing, it is pushing the atmosphere out of the way in order to accommodate that increase in volume, which means that the system is doing work on the surroundings. So when heat is being transferred to the surroundings from the system, or work is being done on the surroundings or on the system, the path by which those processes occur matters in terms of how much total heat was transferred or how much total work was done. So as an example of why work can be different depending on the path that you take, if you were to drive your vehicle from point A to point B, the amount of work that your vehicle has to do to get from point A to B would be different depending on the route that you take, right? If you take a straight line route to go to the grocery store, that's going to take a lot less work than if you visit your friend first and then go to the grocery store. Okay, so that is called a path function. And in this slide, we're going to talk about a state function. So a state function depends only on the current state of the system and not on the path used to arrive at that particular state. So they only depend on the initial state and the final state, not on the path. So internal energy, or E, is a state function. So it only matters where you started and where you ended. So you can figure out the change in the internal energy just by measuring the initial internal energy and the final internal energy. Other examples of state functions are temperature, pressure, and volume. Okay, so the change in temperature of a system is only going to depend on where you started and where you end up. It doesn't matter how you got there, right? If you're going from 0 degrees Celsius to 100 degrees Celsius, it doesn't matter if you go from 0 to 100, or if first you go down to -5, then you go up to 150, then you go down to 100. That change is still going from 0, the initial state, to 100, the final state. Now, examples that are not state functions, Q and W, so heat and work. And you might notice, and this I think is mostly true, is that state functions are usually represented by capital letters, and path functions, or functions that are not state functions, are usually represented by lowercase letters. So we've talked a little bit about work. Now let's talk a little bit about heat, or thermal energy. So what is heat? What is thermal energy? It is the kinetic energy associated with the random motion of atoms or molecules. And this motion is proportional to the temperature of that particular system. So molecules have 3 different ways that they can move. There's translational motion, so molecules can move in space. There is rotational motion, and there's vibrational motion. Okay, so bonds stretching and bonds compressing. So the more motion a molecule has, whether it's vibrational, rotational, or translational, the more heat or the more thermal energy that is associated with that particular molecule. So increasing the heat increases all these types of molecular motions. Okay, so when we're discussing thermodynamic systems, we have to indicate how this system can interact with the surroundings. So thermodynamically, we speak about energy being transferred to systems and surroundings, or from surroundings to system, but it's important to indicate how that can happen. So there's three different ways or three different types of systems that we can talk about. The first type of system is an isolated system, and that's one that's completely shut off from its surroundings. So none of the energy from the system can be transferred to the surroundings, and matter also can't be transferred to the surroundings. Now, essentially, these systems don't exist because nowhere in the universe can you have a situation where energy just can't move. Okay, it's always going to be transferred somewhere, either from the surroundings to the system or from the system to the surroundings. In our everyday lives, the thing that most approximates an isolated system would be a thermos. But of course, you can't leave your hot soup in a thermos forever and expect it to remain hot. It will eventually cool down to room temperature. Now, a closed system is one in which only energy can flow between the system and the surroundings. So thermal energy, for example. So if we have a system such as this, where we have a cup of soup with a lid on it, only energy can be transferred, right? Only that heat energy can be transferred from the system to the surroundings. Now, if we have an open system, energy and matter can flow freely from the system to the surroundings or vice versa. So in that case, we could have this situation here. So an open cup of soup in which both energy and matter can be transferred between the system and the surroundings. Now, reactions are classified as to whether they give off or absorb energy, usually in the form of heat or thermal energy. So we can talk about an exothermic reaction or an endothermic reaction. So an exothermic reaction is one in which energy flows from the system to its surroundings. So if you were to experience this type of reaction or to feel a reaction vessel that is experienced in an exothermic reaction, to you that would feel hot because the reaction itself, the system, is releasing heat to its surroundings, which in this case would be the beaker, your hand, for example. So if it's releasing energy, you're going to feel that as heat. On the other hand, if a reaction is endothermic, then energy is flowing from the surroundings to the system. So if you were to feel that particular reaction or a beaker that contained that reaction, to you that would feel cold, because the system is absorbing heat from your hand. So now that we know a little bit about how heat is transferred, let's talk about work. So in this case, we're going to be talking about pressure volume work. And that is the work done when gases expand or are compressed under external pressure. So if we just go back a couple of slides, remember that work is greater than zero when the surroundings do work on the system, and when the system does work on its surroundings, work is less than zero. So if we look at a diesel engine, we actually have a situation where we have a continuous alternation between the system doing work on the surroundings and the surroundings doing work on the system. So initially, when fuel is being pumped into the cylinder and the piston is pushing against that fuel mixture, so it's compressing the gas mixture, doing work on the system. And on a diesel engine, what happens is when the gas is compressed, well, actually when any gas is compressed, it heats up, thereby increasing its internal energy. And diesel in particular, once it reaches a certain pressure, it gets hot enough that it will spontaneously ignite. So now, since the internal energy has obviously increased quite a bit, that extra ignition is now increasing the heat even further, which increases the pressure on the piston, which then pushes the piston down. Now the system is doing work on the surroundings and thereby increasing the volume of the cylinder once again. So when we're talking about pressure volume work, or PV work, work is equal to negative P times delta V. And the negative sign is there to ensure that when the system is doing work on the surroundings, that the work term is going to be negative. So if we just look at this situation again, initially we have a large volume going to a small volume, right? So this is when the surroundings are doing work on the system. So if our final volume is less than our initial volume, our volume term is going to end up being negative. So if we have a negative delta V, in order for work to be positive, we have to have this negative sign to make sure that work is positive when the surroundings do work on the system. Now with the other way around, when the system is doing work on the surroundings, our initial volume is small, our final volume is large. So now our final minus initial volumes is going to end up being a positive number. So in order to make sure that the work term is negative, we have to have that negative sign on the work term again. Because remember, delta E equals Q plus W. And if we replace W with this minus P delta V term, we end up with this. Our internal energy, our change in the internal energy, equals Q minus P delta V. So let's just go through a quick example. So we have a tank of compressed helium used to inflate 100 balloons, and the atmospheric pressure is 1.01 atmospheres. If each balloon is inflated with 4.8 liters of helium, how much PV work is done by the compressed helium? So here we're focusing on the work done on the atmosphere, right, on the surroundings, because the system, the helium balloon, is what's expanding into the atmosphere. So from our previous slides, we know that W equals minus P delta V, and we know what the pressure is, so work is going to equal minus 1.01 atmospheres, and the change in the volume is going to be initially 0 because the balloon has no volume and no helium in it, and it's finally going to be 4.8 liters per balloon. So we're going to have to multiply this by 4.8 liters for one balloon, but then since we have 100 balloons, we're going to have to multiply that by 100 balloons. So this equals minus 484.8 liter atmospheres. But we want to have this in joules. So if we go back a slide, we'll see that 1 liter atmosphere equals 101.325 joules. So now we could convert this number, our minus 484.8, into joules by multiplying it by 101.325 joules per liter atmosphere. And then what that equals in joules is minus 4.9 times 10 to the 4 joules, or minus 49 kilojoules. So how do we know that this makes some sense? Well, we know that work is being done on the surroundings, right? The system is doing work on the surroundings, so we should end up with a negative value for work, and that's what we get. So now let's talk about enthalpy and enthalpy changes. Now, most chemical and physical processes take place at a constant pressure, so then we can use this term enthalpy, or H, to track the energy changes and the heat flow into or out of a system in terms of thermodynamics. So if we want to define enthalpy, H is going to be the sum of the internal energy plus our PV work. So we can't really measure enthalpy alone. What we would do is to measure a change in enthalpy of a chemical reaction or a physical change. So the enthalpy change is equal to the amount of heat transferred into or out of a system during the reaction or physical change. Again, it has to be at a constant pressure. So if we try to figure out what delta H is, we have our delta H going to be equal to the change in the internal energy plus our P delta V, so our pressure volume work, and delta H ends up being equal to the heat, or Q, at a constant pressure. Now this equation here might look a little bit familiar, especially if you change delta H with Q. So let's just do that. Q equals delta E plus P delta V, right? We already have an equation that uses these three terms, or four terms. Let's just rearrange it so we can see what we had before. Delta E equals Q minus P delta V, right? So in this case, we're just essentially replacing the Q with our delta H, and this is valid as long as we're at a constant pressure. Now, we talked previously about exothermic and endothermic reactions, and that is related to this enthalpy term. So if a reaction is exothermic, we say that the enthalpy is negative or less than 0, so delta H is less than 0. And if a reaction is endothermic, then delta H is greater than 0. So since enthalpy is a measure of the heat flow into and out of a system, we can also look at how this enthalpy change looks when we're talking about phase changes. And when we're talking about phase changes, we'll be talking about a solid to liquid phase change and a liquid to gas or liquid to vapor phase change. So when we're talking about a solid to liquid conversion, So this is going to be at the freezing point of a particular liquid. Then we're talking about the delta H of fusion, or the enthalpy of fusion. And when we're talking about the liquid to vapor conversion, this is going to be at the boiling point of that particular liquid. We'll be talking about the enthalpy of vaporization. Now, when these values are reported in tables, they're reported as per mole of a substance converted. So everything is going to be in joules per mole, for example, if we're talking about an energy or a delta H. So I'm just going to zoom up on this table just to give you an idea of the differences between the delta H of fusion and the delta H of vaporization. So the first four compounds here, methane, ethane, propane, and butane, those are all compounds that, if you remember from intermolecular forces chapter, are nonpolar, and the types of intermolecular forces that they experience are London dispersion forces. So when we have a solid turning into a liquid, we have a specific amount of energy that is required to do that per mole of substance. And if you look at the delta H of vaporization, for the same 1 mole of substance, notice that it is quite a bit greater than the delta H of fusion. So melting a solid doesn't take as much energy as turning a solid from a liquid into a gas. And you can see that with all of these examples of nonpolar substances. And if we look at the next 4 substances, or next 5, methanol, ethanol, acetone, ammonia, and water, you should remember these as all being polar, and in particular, they experience hydrogen bonding. So the forces keeping them together are a lot stronger than the forces keeping the previous 4 compounds together. So if you look at their delta H of fusions, notice they're quite a bit larger than the preceding compounds. And the difference between the delta H of fusion and the delta H of vaporization for all of these is also greater than the difference between delta H fusion and delta H vaporization for the nonpolar compounds. And this has to do with the strengths of the intermolecular forces. So with the polar compounds, it requires more energy to break those polar bonds. So the delta H of vaporization should be higher. It should require more energy to turn that compound from a liquid into a gas compared to a compound that is nonpolar and undergoes only London dispersion forces, which again are a lot weaker than hydrogen bonds or dipole-dipole interactions. So now let's just look at how this energy is transferred to a system as, say, water goes from ice at minus 18 degrees Celsius to boiling and beyond. So here's a graph that shows that change. So we have the energy added on the x-axis and the temperature of the system on the y-axis. So if we start at minus 18 degrees Celsius and add a little bit of energy, we're going to get to a point where the ice is starting to melt. So at its melting point, it is now undergoing a phase change from solid to liquid. So we're at a point where we're continuously adding energy to the system, but the temperature is not changing. Right? So as long as this phase change is occurring, the temperature will remain at 0 degrees Celsius, even though we're continuously adding more energy to the system. Once all the ice has melted into liquid water, then we can now heat up the water until it reaches its boiling point, 100 degrees Celsius. After it reaches its boiling point, we have the same situation where the temperature is not changing, even though we're continuously adding more energy into this system. After we've boiled off all the water, then the vapor can continue to increase in temperature. Now remember the relative sizes of the delta H of fusion and the delta H of vaporization. This flat line here represents the delta H of fusion, and this flat line here represents the delta H of vaporization. Notice that one is quite a bit larger than the other, which matches with what we've seen from the previous table, right? Delta H of fusion is a smaller number than the delta H of vaporization, meaning that it takes less energy to melt the ice than it does to turn the water into a gas. And the main reason for that is when we're turning a solid into a liquid, we're not completely breaking the intermolecular forces. We're breaking them a little bit such that the water is no longer in its crystal lattice form, but water itself still has intermolecular forces that are holding it together in its particular shape. As soon as those intermolecular forces are broken, especially for water, because it has hydrogen bonds, and those intermolecular forces are really, really strong, because we are breaking them at the boiling point, we're completely breaking that intermolecular force. That's going to take a lot more energy. And again, that is shown by both this graph and the value for the delta H of vaporization. So another way that we can relate temperature change and heat flow is to introduce this term called the heat capacity. So the heat capacity of a substance is the energy required to raise the temperature of it by 1 degree Celsius at a constant pressure. So we're talking about an object, right? So it could be a glass of water, it could be a piece of paper, it could be anything else. So how much energy does it take to increase the temperature of that particular object by 1 degree Celsius? That's called the heat capacity. Now the specific heat, or the specific heat capacity, is related to 1 gram of a substance. So we have the same mass of a substance and how much energy is required to increase the temperature of 1 gram of a substance 1 degree Celsius, whereas molar heat capacity is measured per mole of a substance. So we use heat capacity or specific heat to relate the temperature change of a substance to the amount of heat absorbed or lost by that substance. And we can relate temperature to the change in heat through this equation here. So Q equals Cp, Cp again being the heat capacity, times the change in temperature. And we can measure heat capacity in terms of a mass or in terms of moles. So if we just replace the Cp with an mc sub s, meaning the mass of the substance multiplied by its specific heat, or n c sub p, where n is the moles and Cp is the molar heat capacity. So both specific heat and molar heat capacity are intensive properties. So they depend on the physical state of a substance. So intensive properties was something you learned right at the beginning of General Chemistry 1. So if we zoom up on this table, we see that it is a table of specific heat and molar heat capacity values. And we have on the top of this table a number of different solids. So we can see that different substances have different heat capacities, whether it's the specific heat capacity or the molar heat capacity. So the larger this number is, the greater the heat capacity, or the greater its ability to hold on to heat without actually heating up. All right, so it's going to take a lot more energy to heat up something with a higher heat capacity than it will to heat up something with a lower heat capacity. So the phase differences become most apparent on this table when we look at water, since that's the only one that actually shows 3 different phases. So we have a solid, liquid, and a gas, and you can see that the specific heat of each phase is different, as well as the molar heat capacity of each phase. And you notice that the heat capacity of water is greater than the heat capacity of ice and the heat capacity of vapor. So it means it takes a lot more energy to heat up 1 gram of water than it does to heat up 1 gram of ice or 1 gram of water vapor by 1 degree Celsius. And remember, if we go back to those graphs that we saw previously when we were talking about delta H of fusion and delta H of vaporization, delta H of vaporization was a much larger number, and that is reflected in this heat capacity. It takes a lot more energy to increase that water from 100 degrees Celsius to 101 degrees Celsius than it does to heat ice from 0 degrees Celsius to 1 degree Celsius. So now let's go back to our example of turning snow into boiling water. So how much energy or heat would it take to convert 275 grams of snow with an initial temperature of minus 18 Celsius into boiling water at 100 degrees Celsius? So if we follow the heating curve, we would have to go through a few different steps. So it's not just one simple calculation to figure it out. So the first step we would have to go through would be heating the water from minus 18 degrees Celsius to 0 degrees Celsius, which is this portion of the curve right here. So since we're not at a phase change, we can use this equation here, Q equaling the mass of the substance times the specific heat capacity times the change in temperature. So we're going to use the specific heat capacity because we're given a mass in the equation. We could use molar heat capacity. We would just have to change that mass into moles. And we have to use that mass because remember, specific heat capacity has to do with 1 gram of a substance. And we have 275 grams here. So we have to multiply the specific heat capacity by the mass to get the total heat capacity of that particular substance. So next step, once the snow has reached 0 degrees Celsius, is at a phase change. So now the snow is melting into water. So we're on step 2. And since we're at a phase change, we have to deal with the heat of fusion. So here we are, this step right here, the flat line. Remember, this is delta H of fusion where we're continuously adding energy, but the temperature is not changing. So we're not going to have a delta H in this term. So in this case, Q is going to equal delta H of fusion times the moles of substance. Now we need moles of substance again because delta H is always a per mole value. So this is going to give us the amount of energy required to melt 275 grams of snow at 0 degrees Celsius. Now the last step to get it to boiling would be to heat the water from 0 degrees Celsius to 100 degrees Celsius. So now we're looking at this step here from C to D. Now again, we're not at a phase change, so we don't have to worry about a delta H. Q is going to again equal the specific heat capacity times the initial mass of snow times the change in temperature. Change in temperature is going to be 100 degrees Celsius. And our heat capacity in this case is going to be different, right? Because initially we had the heat capacity of solid water, of snow, of ice, right? That's different than the heat capacity of liquid water. Now, if we add all of these together, Q from step 1, step 2, and step 3, that's going to give us the amount of energy that's required to heat 275 grams of snow with an initial temperature of minus 18 Celsius to its boiling point at 100 degrees Celsius. Okay, so let's just go through a quick example. So how much energy must be absorbed by 100 grams of water to raise its temperature from 30 degrees Celsius to 100 degrees Celsius? So we need to recognize that we're not at a phase change, so we don't need to worry about delta H fusions. We're asked how much energy, so we're going to need to figure out what Q is. And if we're adding energy to the system and we're trying to heat it up by a specific amount, we're going to be needing the heat capacity. So since we're using a mass in the question, 100 grams, we'll use the specific heat capacity. And also, since we have mass, we're going to have to multiply that by mass. And we have our change in temperature, which is 30 degrees Celsius to 100 degrees Celsius. So now let's solve this problem. So we'll solve for Q equals 100 grams. And the specific heat capacity of water, if we look on the slide from a couple, and the specific heat of liquid water from a couple slides ago is 4.18 joules per gram degrees Celsius. So that's our specific heat capacity, and our change in temperature is going to be 100 degrees Celsius minus 30 degrees Celsius. So solving for Q, we end up with 29,260 joules, or if we convert that to kilojoules, 29.3 kilojoules. So that's how much energy is required to heat 100 grams of water from 30 degrees Celsius to 100 degrees Celsius. So that's all I have for this video. If you have any questions, please feel free to contact me.